work again?
All right. Hope that does.
Yes. All right. Tim, I think we're good to start the live stream. That means we've started it. Great. So it's my pleasure to introduce Robert Brandom, Distinguished Professor of Philosophy at the University of Pittsburgh. He's going to talk to us about the logical expressivism and articulating the structure of reasons. Thank you, Robert.
Thank you, Chris. It's a pleasure. I'm going to present two technical results today, but mostly introduce you to the philosophical context in which I find them potentially significant. I'm a semantic inferentialist. I think of the meaning or propositional content expressed by ordinary declarative sentences in natural languages, at least, to consist in the role those sentences play in reasoning. And I think an essential part of understanding a claim is knowing what follows from it, what would be evidence for or against it, and so on. I'm interested in the sense of propositional contentfulness that consists in being able both to serve as a premise and as a conclusion of inference. Slightly more specifically, I'm interested in the relations of implication and consequence that determine what counts as a reason for what. The idea is that instead of thinking of propositional contents as a property of sentences, they're having this content or they're being true or false, rather I want to think about their content in terms of their relations to each other. So this is a standard move, of course. Think about the objects in terms of the relations they stand in to one another. Indeed, we'll turn the crank one more time. Think about those relations in terms of the relations they stand in to one another. Also familiar. The question is, what tractable conceptions of propositional content can be elaborated from the role sentences play if all we're looking at is the relations of implication or consequence that they stand into one another? What kind of logic or semantics could we do with them? Now, there's special features of this case. To begin with, the sentences don't have consequences typically all on their own. The inferences we're interested in are multi-premise inferences, sometimes massively multi-premise inferences. Really, we should think about the implication relations as holding between sets of sentences. We're really talking about a consequence relation just as a binary relation on the power set of some lexicon of sentences. So we have a basic relational structure that has that lexicon set of sentences, and then some distinguished set of pairs of sets of sentences, a binary relation on them, thought of as the good implications, the ones whose first element, thought of as premises, provide reasons for, good reasons for the second set, thought of as the conclusions. But, when I say the consequence relation is just a binary relation, well, presumably not just any binary relation is going to count as a consequence relation, and certainly not everyone is going to give rise to a tractable notion of propositional content. So, at least for philosophers, it's natural to look to logic. Logic is sometimes thought of as the mathematical study of consequence relations. So we could hope that they would help us in saying something about how to pick out the consequence relations. And there is a consensus about the structure of specifically logical consequence relations. Just about 90 years ago, in the mid-30s, Tarski wrote his classic paper on the concept of logical consequence. Gensen, the founder of the proof theoretic tradition in logic, within a couple of years, came up with essentially the same set of structural conditions. Tarski, having made this advance of thinking about consequence relations algebraically, came to the conclusion that they needed to be topological closure operations. And basically, these are the three conditions he imposed. Containment, that says that the set of consequences includes the set of premises. Among the things the premises could give reasons for are themselves. Monotonicity says that if you've got a good implication, throwing in more premises doesn't make it a bad one. And transitivity shows up in this setting as an idempotence relation. It says if something's a consequence of a consequence, then it was already a consequence. As I say, Gensen, not working with sets but with lists, essentially has the same set of structural conditions. The trouble is, there's a structural mismatch between those conditions, the topological closure conditions, and the actual structure of implication relations, if we're thinking those implication relations as codifying ordinary senses of is a reason for. In law, in medicine, reasons are probative rather than dispositive. They're defeasible. Though we don't find containment being violated, it's not unusual to find monotonicity and transitivity violated in ordinary reasoning. Now, there's a temptation to think the sense of good reason, which I'm marking here with this funny snake, with this funny snake turnstile. You may think that that's just too flabby a notion of reason to be getting on with. But as a philosopher, I'm interested in codifying this notion of reason, or anyway, notions of reason that we find in the wild, which don't seem to meet the full structural conditions. These structural conditions are built fairly deeply into the mathematical apparatus that we're using to represent these things. If you're thinking of consequence in terms of some property of the premise set that's preserved when you move to the conclusion set, then you're going to build in transitivity. If you think model theoretically, the way Tarski came to, that to say this premise set implies the consequence set is to say that every model of all the premises is a model of the conclusions, then you're going to build in monotonicity, throw in more premises, you get fewer models, more inclusions. If we model the good implications by the morphisms in a category, we're going to build in transitivity. Again, this structural mismatch raises an issue. Is there anything that logic can tell us about these non-transitive, non-monotonic, at least in a global sense, relations? So I think the answer is yes. We can still use logic, but we need to think about logic a little bit differently. I'm going to suggest we need that there's sort of three different perspectives we need to take on it. And the first one is, don't worry about pure logic. Don't worry about the structure of logical consequence. Worry about what logic teaches us about consequence when it applies to a substantive theory. That is, when the logic applies not just to instances of reflexivity, A implies A, but to substantive non-logical implication relations. I'm suggesting that we should think about logics as functions that take as their arguments one consequence relation and produces their values another consequence relation. If we start with a pre-logical base vocabulary, a lexicon, and a binary relation on the power set of that lexicon, we're starting with a logically atomic lexicon, L0 here. We've got syntactic rules that extend the one lexicon to a logically complex lexicon. It says, if A and B are in the extended lexicon, then so is their conjunction, the conditional relating them, the disjunction, and so on. And then the guts of the logic are the semantic rules that determine a function from the consequence relation that applied to the atomic sentences to the reason relations, the implication relations that hold of its logical extension. So where Tarski made a conceptual advance just by thinking about consequence relations as algebraic objects, Gensen goes farther and thinks about particular instances of implication relations, particular implications, he'll call them sequence, as objects, and looked at how we could mathematically manipulate these sequence. In particular, if we have a sequence that says the premise set gamma implies the conclusion set delta, we can impose sequent rules that are meta-inferential, that tell us that if one implication is good, then another one is good. So, for instance, Tarski's monotonicity condition that if premise set X is a subset of premise set Y, then the consequences of X are a subset of the consequences of Y, becomes Gensen's rule that if a sequent gamma implies delta above the line, if that's a good sequent, then so is gamma together with any other further set of auxiliary premises implying the same conclusion. That's also a good implication. So the sequent rules are meta-inferential. They're telling us about the relations between instances of the consequence relations. The key here is that sequent rules can be applied to two kinds of sequence. Those that hold just in virtue of their structure. If you apply the rules of a sequent calculus just to instances of A implies A, you get the purely logical implications. But you can also apply it to a substantive implicational theory, a set of implications involving logical atoms, which are materially good, that is good in virtue of the concept of their non-logical concepts. So Berkeley's to the west of Pittsburgh, so Pittsburgh is to the east of Berkeley. That's good. It's not logically good. It's materially good because of the content of the concepts east and west. And similarly, it's raining, so the streets will be wet. Though that's a good implication in virtue of the concept raining and the concept wet. We can start with a substantive theory like that and elaborate it using meta-inferential sequent rules. That's the first change of perspective I'm suggesting. Second, we can ask, well, if we're thinking of the logic as a set of meta-inferential rules, defining a function from one consequence relation to a consequence relation on a logically extended domain, why are we doing that? And what are the criteria of adequacy for doing it properly or well? Why are we doing logic anyway if we're thinking not about the pure logical consequence relation, but about the applied one? And here the second idea, this is the logical expressivism of my title, is that the point of introducing logical vocabulary isn't a matter of what it lets us prove, it's a matter of what it lets us say. It's the expressive power that it gives us. It's more important than what follows logically is the expressive capacity that conditionals and negation let us give us to say what follows from what and what's incompatible with what. The characteristic defining expressive task of logical vocabulary, I'm saying, is to express reason relations, in the first instance of implication, explicitly in the form of claimable propositional contents of logically complex sentences. We can see roughly how that works by looking at one of Genson's rules, the detachment rule. It says that if gamma together with A implies delta together with B, if that's a good implication, then so is the implication by gamma of the conditional, if A then B, in that same context, delta. That sequent rule that says that if the sequent above the line is a good one, then so is the sequent below the line. In fact, this one goes both ways. That gives us a fairly clear sense in which gamma, having A arrow B as a consequence, says that B is implied by A in the context gamma, or the context gamma on one side, delta on the other. And there's we can tell a similar story about how implication of negations codifies incompatibilities in the form of inconsistencies, and so does for reasons against what implication does for reasons for. So this logical expressivism motivates an expressive ideal for logic. The ideal logic would be a set of semantic rules, semantic in that they're defining a function from consequence relations to consequence relations, that elaborate the reason relations of a base vocabulary into the reason relations of its logical extension, its extension to the logically complex sentences formed from those base sentences. And the ideal logic would have the expressive power to make explicit the reason relations, the consequence relations of any base vocabulary. Ideally, it would do that regardless of what structural conditions the base vocabulary satisfied. Non-monotonic, non-transitive. We'd still like to be able to introduce conditionals to say that an implication is good. So I say the expressively ideal logic would be universally LX. L for elaborated from and X for explicative of any constellation of reason relations, any implication relation at all, regardless of its structure. That's what an ideal logic would do. So the third idea, and this is subtler than the other ones, but I think it'll become clear as I go along. We want to consider different sets of connective rules, different logics that work even if you don't have the various structural rules in place. We want to compare the expressive power of connective definitions under substructural circumstances. There are two kinds of sequent rules: the structural rules that don't depend on anything about what particular vocabulary occurs in the sentences. So for instance, here's the cumulative transitivity, the cut rule. It says if gamma implies A and gamma together with A implies some delta, then gamma already implies delta. Doesn't matter what connectives might or might not occur in those sentences. But they're connective rules which do depend on the occurrence of logical connectives in the premises or the conclusions. We're talking about looking at sets of connective rules that continue to have good expressive features, even if we deny the structural rules. The strategy is to compare the result of relaxing the structural rules on the consequence relations that we get by applying different connective rules and look for the ones that have the greatest expressive power, and furthermore, where they degrade gracefully or continue to have that expressive power under substructural conditions. And we've got a favorite logic. There is one that is structurally ideal, expressively ideal under these circumstances. My collaborator, Daniel Scott Kaplan, realized that we could exploit reversible rules, which Genson's only student, Kettinen, had come up with already in the early 40s. By tweaking those rules, we could come up with a remarkably expressively powerful logic. We call it NMMS, non-monotonic multi-succedent logic, which retains its expressive power even when we go substructural. The only structural condition that turns out to matter for this expressive power is containment, CO. Monotonicity and transitivity we can do without. Now, here are the rules of NMMS. Unless you dance with these secret calculi all the time, that probably just looks like gibberish. The details of it don't matter. I'll talk about what features of it we do care about. It has three remarkable features, this logic. It's expressively complete in a very strong sense. And here's the sense. It can say of the base that any particular set of atomic implications holds in it. For any implication, any sequent involving logically complex sentences, we can compute a set of base sequence such that this sequent in the logically complex language is a good sequent just in case it's NMMS elaborated from a base that includes these atomic sequence. For every sequent in the logically complex vocabulary, we can assign it its image in the base, the set of things in the base, such that them holding in the base is necessary and sufficient for this sequent to hold in the extended language. And in that sense, the logically complex sequent, which involves all sorts of conditionals with negations embedded in it and so on, pick any arbitrary sequent in the logically extended language, we can say exactly which sequence in the base need to hold for it to hold. This is a more flexible and powerful version of the feature we already saw in a two-valued sort of tabular, truth functional version of classical logic, where for any complex sentence, we could say, well, if it's true, then exactly these base sequence must have these truth values. And if these, if you give me truth values for the base sequence, I can say what logically complex sentence is true just in case they have that. What we're doing now is saying, is giving a result like that, but for atomic implications and implications in the logically extended language. For any given implication relating logically complex sentences, it's settled just which implications involving atomic sentences must be good for it to be good. That's our sense of express, explicative, the sense in which the sequence in the logically extended vocabulary are saying of the base vocabulary sequence that they hold. And this expressive power is universal across the NMMS extensions of any base vocabularies for which CO holds. That's the minimal condition. And here's the third remarkable feature. NMMS is essentially just classical logic. If you do impose all of the Tarski-Gensen structural conditions, if in addition to CO you impose monotonicity and transitivity as global structural requirements, then as gnarly as the NMMS connective definitions look, they determine exactly the same logic that Gensen's LK definitions do, namely classical logic. The difference is that when you go substructural with essentially any other specification of classical logic besides this one, if you apply that to a base vocabulary that's non-monotonic, it won't be conservative over it. The monotonicity is built into the connective definitions enough to keep it from being conservative. Whereas the NMMS version, under full structure, it determines exactly the same consequence relation, but when you relax structure, all these connective definitions that determine the same consequence relation under fully structural conditions determine quite different consequence relations when you relax the structure. NMMS is the one that still is a conservative extension and is expressively complete for them. So that's the first result I wanted to put on the table. Notice that NMMS is not a non-monotonic logic. It's a logic for codifying non-monotonic and non-transitive consequence relations. And it turns out that to do that, the logic doesn't need to be non-monotonic. The purely logical consequence relation of NMMS just is classical logic. We can get to that purely logical consequence relation two ways. If we say, well, what consequences are good no matter what base you apply them to, as long as the bases satisfy CO, well, that consequence relation, that's the consequence relation of classical logic. Or we can ask, what happens if you apply the connective definitions of NMMS to to the base vocabulary that just has instances of CO in it? Well, again, you just get classical logic. And further, if you apply these rules to any material base that satisfies CO, the consequence relation you get will be supraclassical. All the classical theorems will still be theorems. So this was the subtler third shift of perspective in thinking about logic I was talking about. Logics, thought of as the function from consequence relation to consequence relations, that are equivalent when applied to fully structural bases and with the structural rules stipulated. Logics that are equivalent under those circumstances come apart, determine a wide variety of consequence relations, some of which have these good expressive powers, and some of those retain those expressive powers even when we go substructural. So NMMS is our candidate for the expressively ideal logic. Okay, now I want to move over to think about semantics. We can logically codify substructural consequence relations, introduce conditionals to talk about them, uh, give an expressively complete logical account of them. Can we also do inferentialist semantics with them? Do these substructural consequence relations uh, confer on the sentences that play suitable roles as premises and conclusions in them? Do they confer tractable notions of propositional content? Can we get a notion of role in reasoning where the reason relations are massively substructural? Can we get a tractable notion of propositional content uh, out of them? We're starting with this notion of vocabularies, these relational structures. We've got uh, the set of what I'll call an implication space of candidate implications, which are just pairs of a premise set of sentences and a conclusion set of sentences. Uh, and we pair those with uh, a set of a distinguished subset of that implication space, the good implications, according to that frame. That's the binary relation on them. And now here's the fundamental uh, idea of the semantics. I said it was part of the motivation of semantic inferentialism that at least an important part of what you need to be able to do in order to count as understanding some claim is be able to make some distinction between what would follow from that claim and what doesn't, what it would follow from and what it doesn't, what it's incompatible with and what it's not. You have to know your way around in the space of implication relations in which that sentence is involved. So to understand a concept like lion, you need to know that they're materially good implications of the form. Uh, the lion's really hungry and it sees a wounded antelope nearby. So the lion will chase the antelope. Uh, you don't need to be infallible, and there may be many of the implications involving, say, the concept molybdenum that you don't know whether they're good or not, but you got to make some rough and ready division of the material implications involving some concept, some rough sorting of them into good and bad in order to count as having the concept lioness or molybdenum. But it's you need to be able to do more with these implications than just say, oh yeah, that implication that the hungry lioness who sees the wounded uh, antelope will chase it. You need to know something about what other circumstances would interfere with that implication, would defeat it, or wouldn't. So you need to know, well, the conclusion that it would chase the antelope wouldn't follow if uh, the lioness were struck by lightning, uh, or probably if the antelope were struck by lightning. But uh, if today were Tuesday instead of Thursday, that would make no difference to the implication. That is, your mastery of the inferential role of a sentence doesn't just involve being able to make yes or no judgments. Is this a good implication or is that one? However, uh, fallibly and incompletely, you also have to associate with each one something like a range of subjunctive robustness. You got to have some sense of what alterations to the premises would keep it a good implication or make it a good implication if it's not a good implication, and which ones would defeat it or be irrelevant to the holding of it. So in our spare representation of consequence relations as binary relations on the power set of a lexicon, we get a notion of a range of subjunctive robustness. Uh, Now, we're using this notion to semantically interpret implications. That is, the semantic inferentialism is going to go so deep that it's not just we'll interpret uh, sentences by associating sets of implications with them, though that is what we're doing. We also see the interpretation of sentences as less fundamental than the semantic interpretation of implications. And here we're associating, as the semantic interpretant of an implication, we're associating its range of subjunctive robustness. Think of that as the set of premises that uh, you can add to a good implication and keep it good, or if the candidate implication you're semantically interpreting isn't good, these are the premises that if you threw them in, it would be good. Because we're working in a multi-succedent setting, we can fiddle with the conclusions as well as the premises. But to get the sense of it, just think about the premises. So we've already associated something like a truth value with the implications. That is, we've got candidate implications, a set of sentences as a premise set, and a set as a conclusion set. For any one of those, it has a value. It's either good or it's not good. It's either in the set I of distinguished good implications or it's not. That's like the truth value of a sentence, only for implications. The intention of a sentence in the truth setting is its truth conditions, a function from something to its truth values. Our intention is going to be the range of subjunctive robustness of a candidate implication. That is, if it is good, what implications, what premises and conclusions can you add to it to keep it good? And if the candidate implication we started with wasn't good, what additions to it would make it good? We have these, we're now associating really with each set of implications its range of subjunctive robustness. Those are the other implications that if you combine them with all of these implications, you get just good ones. And then we can associate with each implication or set of implications as its implicational role. We can just form equivalence classes of these accordingly as they have the same range of subjunctive robustness. And now, having interpreted the implications, we can interpret sentences as pairs of sets of implications. Dummett understands sentences in terms of their circumstances of appropriate application and their consequences of appropriate application. You got to know what's a reason for making the claim, and you got to know what making the claim is a reason for. We just do that. We can associate, this apparatus lets us associate with a sentence its role as a premise, that is, all the good implications in which the sentence A appears in the premise set. We can specify that if we just take this base implication that has just A on one side and the empty set on the other side. Its range of subjunctive robustness is all the good implications in which A appears as a premise. And on the other side, we get the set of all the implications in which A appears as a conclusion. So we can think of the semantic interpretation of a sentence as the pair of its premissory and its conclusory role. And those we can think of as the roles of these sort of skeleton implications. So we're determining ranges of subjunctive robustness, which is a set of implications that you can conjoin with these to get good ones. We can define roles with respect to them, and we can define sentences in terms of them. This is just rehearsing that. Now, thinking propositions that way, just to get a sense of it, the negation rules of NMMS, just the classical rules. If gamma implies A, then if gamma implies delta and A, then gamma together with not A implies delta. The left rule says that the role of not A as a premise is the same as the role of A as a conclusion. And the right rule says the role of not A as a conclusion is the same as the role of A as a premise. And that means we can semantically interpret not A just by flipping the valences, taking the conclusory role of A as the premissory role of not A, and vice versa for the conclusory roles. Now we can operate on these implicational roles. We have a intersection-like operation and a union-like operation. Simjunction just takes the role of the union of two sets, and adjunction is a little bit more complicated. We join the implications together and then take the roles of what we get. The details of these definitions don't matter much. We're operating on, conceptually they don't matter much. The details obviously do. We're operating on implicational roles to determine further implicational roles in aid of operating on the representations of sentences to get the representations of other sentences. And here, let me just plunk down as a deus ex machina, this set of semantic definitions in terms of ranges of subjunctive robustness and implicational roles. This set of semantic definitions is sound and complete as a semantics for NMMS and its sequent definitions. Now, these things don't look a lot alike. Here we're operating on roles of sentences with respect to ranges of subjunctive robustness. Here we're just imposing recursive rules. If the sequence above the line are good, then the sequence below the line are good. But both of these are codifying a set of metainferential rules, a way of computing the implications of logically complex sentences from the implications involving only the atomic ones. And it turns out that these are systematically related ways. That is, not only does this apparatus produce a sound and complete semantics for our favorite logic, NMMS, it gives us a recipe for producing a sound and complete semantics for any logic that you can codify in sequent calculus. And these are the rules. The first element in the semantic clauses corresponds to the left rule of the sequent calculus. The second element corresponds to the right rule. Anything superscripted with a plus stems from sentences that occur on the left. Superscripted with a minus stems from sentences that occur in the right. Adjunction is combining things that happen within a single top sequent. Simjunction is combining them. Here's an example that I hope will give you the sense of it. Let's look at the crucial conditional. On the sequence side, we've got a left rule and a right rule. And those correspond on the implication space side to the first element and the second element in are semantic representations of them. Now, the sequent rules only deal with what's above the line. They're telling you what function of what's above the line, will give you the role of A arrow B as a premise. And here it's saying what sequence above the line give you the role of A arrow B as a conclusion. And if we look at this right rule, we say that adjunction, the union-like operation, is the one that combines the sentences that occur in a single sequent, and that's what we find here. And that the plus means that the sentence came from the premise side. The minus meant that it comes from the conclusion side. If we look at that with the left rule is a lot more complicated. It's got 3 top sequence. Well, that means it's got 3 terms joined by simjunctions. So it does. We only look at the sort of operative atomic sentences. Here's an A that's coming from the conclusion side, so it gets a minus. In the next rule, the B is a premise, so it gets a plus. Final term has an A and a B, so it needs a adjunction. The A is on the conclusion side, so it gets a minus. The B is on the premise side, it gets a plus. That's how these different representations are correlated. Okay, well, that's the second technical result that I wanted to report in the context of why I care about it. Our initial question was, if we generate from some lexicon of sentences the candidate implications, the cross product of the power set of the lexicon with itself, pick a distinguished set of those as the good implications, where the premise set really implies, gives good reasons for the conclusion set. And we asked, well, what structural restrictions are there on the capacity of logical and model theoretic metalanguages to express implication relations in this sense and manipulate propositions that are defined by their implicational roles? And on the side of logic, we found that, well, traditional connective definitions build in monotonicity and transitivity. We can find a logic which has a purely logical consequence relation, is supraclassical when applied to CO-compliant bases, but has this very strong expressive completeness result, that for every sequent in the logically complex language, we can say exactly which base sequence hold in all and only the bases from which NMMS will elaborate that conclusion as a good implication, and vice versa. On the side of implication-space semantics, we defined here the key really was the way we combine the candidate implications, point-wise dual union. We're combining them by unioning their premise sets, unioning their conclusion sets to get a new candidate implication. That's a commutative monoid on this cross product of the power set of the lexicon with itself, has the empty set as its identity. If we then sort implications into equivalence classes accordingly as that commutative monoid maps them onto a set of good implications in whatever model we're working on, we can assign implicational roles to the implications. We can build propositions by taking sets of premissory uh, roles and sets of conclusory roles. And we get a well-behaved um, uh, model theory as well. So both logical expressivism and semantic inferentialism set strenuous requirements for relations to count as consequence or implication relations. The logical expressivism says you got to be able to make them explicit using logical vocabulary, paradigmatically the conditional to make implication explicit. There's a story I haven't been telling parallel about negation and incompatibility, codifying reasons against. And the semantics says, well, and those implication relations must yield a tractable notion of propositional content, one that we can manipulate, for instance, to uh, recursively compute the inferential roles of logically complex sentences from the implicational roles of uh, logically simple uh, sentences. And we want to be able to do that under massively substructural conditions. Um, but it turns out that we can do that. We start not with sentences, but with consequence relations that capture a notion of reason for. And we've shown how logic and model theoretic semantics can understand those implication relations as conferring semantically well-behaved propositional contents on those expressions. That is, the two results I've at least waved my hands at show how to use variants of traditional proof theory and model theory, which normally only work in topologically closed settings, that is, ones that have monotonicity and that assume or enforce the transitivity and monotonicity of the consequence relations. But we've shown how to do the logic and semantics with radically substructural implication relations. And the notion of expressive completeness that we've got makes definite the idea of logical expressivism that the point of doing logic is to let you say what follows from what. Semantic inferentialism is advanced by this implication-space semantics, which is not only sound and complete for the sequent calculus, specifications of that of those logics, but for anything you can specify in sequent calculus terms. Thank you.
Thank you, Bob. Uh, so now anyone who would like to ask a question can definitely raise their hand or unmute themselves. And I can start us off. Uh, so clearly there's something modal about range of subjunctive robustness, and I'm not sure if you could help elaborate the connection to traditional thinking about modal logic or Kripke frames.
Yeah. So we're working in what I'm calling an implication space that's generated by some lexicon. So it's the set of all the pairs of sets of sentences in that lexicon. Uh, and we say, well, one of the things you need to know is which are the good implications? Which ones does the first element, the premise set, really offer reasons for the conclusion set in whatever sense of reason for we're trying to codify at the moment? We say, okay, I think that it's raining, so the streets will be wet. That's one simple relation of singletons here. I think that's a good implication. But that's sort of lighting up one point in this implication space, saying that's a good one. The modal element is asking, yes, but what about its neighbors? What about if you add the premise that I don't know, there's a canopy over the over the road here, well, then it would no longer be good. The thought is that each implication is surrounded by a cloud of neighbors, and understanding your understanding of that one implication depends on your grasp of its neighborhood, of what's going on in its neighborhood. And that's what the ranges of subjunctive robustness tell you. Which of its neighbors are also good? So you can think of it as a kind of accessibility.
Hmm. All right. Well, another question is because I think this idea of the sort of squiggly snake turnstile might be a little new. Should I be thinking about that as sort of because you originally motivated us by legal or medicinal vocabularies, and so should I be thinking about that as like descriptive or normative? Do I associate it with an individual and their dispositions? Do I associate it with what a community would come to agreement over some extended deliberation?
So, I mean, the expressivist ideal is to have a formal apparatus that will let you mean by implies whatever you want to mean and will give you the expressive capacity to say what implies what in that sense. Uh, I, when I'm wearing my philosopher of language hat, I'm thinking of discursive practice as a matter of making claims that express my acceptance or rejection of uh, various propositions, uh, and people in my community making challenges to it, challenging my entitlement to that commitment, and me defending that commitment. They challenge me by giving reasons against the claim I've made. I defend it by giving reasons for it. Uh, Greg Restall and Dave Ripley suggest uh, one formally tractable notion of implication that suits our setting is that gamma in this snaky way implies delta in case the position you're in, if you assert everything in gamma and deny everything in delta, is normatively out of bounds. That's a normative, pragmatic notion of implication, and I think it's a really helpful one. But if you want to think in terms of the dispositions of an individual to endorse various conclusions, hey, we want to codify those that notion of consequence as well. Uh, you're going to need some justification for thinking of uh, the relation between sets of sentences that you're focusing on being a reason relation, where the one set gives reasons for or against the other. But sort of whatever philosophical story you tell about that, I'd like to be able formally to uh, codify that notion and see what uh, concept of propositional content you get uh, if all you know about the sentence is its role in implications in that sense of implication. And the upshot of the story I told today is uh, the structural restrictions on doing that are much weaker than people had assumed. Logic and model theoretic semantics can capture massively substructural uh, implication relations, essentially just as well as they can topologically closed ones. And though I didn't talk about it, there's further sort of weaker structural conditions. Instead of monotonicity, you can have cautious monotonicity, which, while acknowledging that you can't uh, weaken with arbitrary additional premises, says, well, but you can weaken with anything that's already implied. Uh, we can deny that, and NMMS still is expressively complete. The implication-space semantics still will codify um, uh, logics specified in sequent calculi, and so on.
Great. And maybe we can have Janet. Can you unmute?
Yeah, I think this is wonderful. Really enjoy this, and I think it's very useful for the foundations of systems engineering, which is what I'm interested in. And so, could you say something about your book on this that you briefly showed?
Yes. Um, well, it's um, taking these two ideas, the semantic inferentialism that says understand propositional contents as roles with respect to reason relations, and the logical expressivism, uh, and both doing the philosophical motivation for them, talking about the relation to discursive practice in a way that I had to leave off stage here, and really working out uh, uh, what sort of expressive powers we can, on the one hand, capture logically and then understand semantically. So, for instance, an additional bit of logical vocabulary that we talk about in the book. Uh, so, we're interested in thinking about uh, semantic frames where um, the sentences stand in implication relations to one another, and those implication relations are substructural. Uh, well, so in this generally non-monotonic C, there are going to be islands of monotonicity. There are going to be some implications. The A is to the west of B is to the east of A. It's not really defeasible. That one's going to be monotonic, even though it's material. Well, we can introduce a modal operator that uh, lets us make explicit those islands of monotonicity or islands of transitivity or of both, where we mark the implications in the language if it's not just that delta follows from gamma, but it follows monotonically from it. So there's more on offer in the book than just the proofs of the claims that I waved my hands at here.
Very good, thanks.
Great. And so, yeah, we're at the hour. So, yeah, if we can, Tim wants to cut the YouTube feed, we can do that. And also, Valeria has a question.
Oh, hello. Um, Very interesting. I love the fact that we have a lovely defense of logic, kind of very necessary in the days that we're living. But I'm worried because, Gensen, together with Hilbert, are the four founders of proof theory. And Gensen in particular kind of had lots to say about intuitionistic logic, constructive logic. And I haven't seen how that's going to come in your way of seeing things. Can you say something about it?
Okay. Yeah, we're working essentially in the multi-succedent sequent calculus, and go figure, we get classical logic out of it. As I say, there's a sense in which NMMS just is classical logic. If you add the structure, it's just a variant way of specifying that. We can't do implication space semantics with single succedent um, sequence. But we can do NMMS. There's a single succedent version of NMMS, which is supra-intuitionist instead of supra-classical, and which converges, whose degenerate case, whose purely logical consequence relation is just intuitionism. So this general approach is amphibious between the intuitionistic single succedent setting and the classical multi-succedent setting. It's just that in the intuitionist one, we can't prove the kind of expressive completeness result that was my first punchline. We can't because Kettnen showed how to do reversible rules for the multi-succedent classical case, there aren't reversible rules. So we can't trace back for the single succedent case. So we can't trace back to the base sequence that are responsible for the later ones, at least not with the sort of care and completeness that we can get in the multi-succedent case. So this line of thought, I don't know, made us more friendly towards classical logic. You're muted.
Sorry. Yeah, but we're missing an awful lot of the properties that we would like to have, like Curry Howard and stuff like that. So a smaller, further question is, if you have super intuitionistic things, what else does the system get you? What is the extra over the intuitionistic? One kind of restricted to the topologically closed case, as you call it.
Well, I'm not sure if this is a responsive answer to your question, but one of the things we do in the book is talk about role inclusions, where we can have one proposition whose premissory role is a subset of the premissory role of, sorry, if I say Pedro's a donkey, so Pedro's a mammal, the premissory role of donkey, you can replace mammal with donkey as a premise everywhere, saving the goodness of implications, and you can replace donkey with mammal as a consequence everywhere and get and preserve the goodness of implications. In the fully structural case, if the implication goes across the turnstile, then it holds for premissory and conclusory roles as well. But if you go substructural, that isn't the case anymore. One of the things we prove is that the logic of premissory role inclusions is K3, and the logic of conclusory role inclusions is LP. Both of these are the strong Kleene trilogics. The one that's the logic of truth value gaps corresponds to premissory role inclusions. The one that's the logic of truth value gluts, it corresponds to, its consequence relation is the consequence relation of conclusory role inclusions. So those trilogics that have gotten a lot of philosophical interest in the last couple decades, those show up as special cases in this implication space semantics. We can do linear logic. I mean, if you know the Girard's phase semantics for linear logic, that was really the origin of this implication space semantics. So we can do at least the mall linear logics are absolutely straightforward in implication space semantics. But we can handle non-transitive cases, which linear logic can't.
Well, thank you so much.